Welcome to the Deep Dive, the place where we sift through the sources you sent us and surface the fundamental, often surprising truths that define our modern world. Today, we are going on a really deep historical trace of artificial intelligence. But we're not starting in a computer lab.
No, not at all. We're starting in the world of pure abstract mathematics.
Right. Our mission is to understand the absolute first principle, the foundational law that makes all of modern deep learning even possible. We're going to track how one very specific and pretty obscure mathematical theorem from the 1950s provided the proof that underpins every large language model running today.
And that idea of a mathematical foundation is, it's everything. It gets to the very heart of what learning actually is. If you follow the Church-Turing thesis, then everything we call intelligence or computation, it's all fundamentally equivalent to a Turing machine.
Oh, okay.
And if that's true, then the process of learning has to be the mathematical equivalent of, well, of figuring out the input that created a certain output. Our sources call it Turing machine inversion.
That sounds incredibly complex, like trying to run a movie backward to guess the scriptwriter's original idea.
Exactly. It's a great analogy.
Yeah.
But in 1964, a mathematician named Ray Solomonoff proved that this whole complex process of universal learning is mathematically equivalent to something much simpler.
Something we hear about constantly today.
Yes. Next token prediction. The ability to look at a sequence and just predict the most likely next step. That is, theoretically, the engine of all intelligence. So we knew what learning was. The question that almost killed the field for decades was, is there a mathematically valid universal mechanism to actually do it?
Okay, let's unpack this. Because the history of that mechanism, the neural network, is just a wild story. It's this incredible initial promise, then a devastating mathematical
Or
failure,
a death sentence, really.
only to be resurrected by a decades-old proof from Soviet Russia. It's amazing. So
Yeah.
the journey, it really kicks off in 1943.
With the McCulloch-Pitts network, the very first formal mathematical model of a neuron.
And the team behind it is just amazing. You have McCulloch, a physiologist trying to figure out the brain, and his partner, Walter Pitts, who was this genuine math prodigy.
A total prodigy. Taught himself logic and calculus, didn't even have a university degree.
And what did they actually build?
It was revolutionary. They modeled a neuron as a simple binary on or off switch. And they proved, rigorously, that if you had infinite memory, a network of these simple switches was computationally equivalent to a Turing machine.
So that was huge. It meant right from the start that even this simple model could theoretically compute anything a modern computer can. It set the bar for what's possible.
Exactly. And that promise is what fueled the hype cycle of the 50s and 60s around Frank Rosenblatt's perceptrons.
The thinking seems so simple, right? We've got a model of a brain cell. If we just link enough of them together, we get an artificial brain. Rosenblatt was all over the media.
The world was ready for it. But the reality was much more limited. The early perceptron was only 2 layers deep, and that meant it was mathematically stuck using only linear classification.
A limitation that was about to be brutally exploited.
Yes, by Marvin Minsky in 1969. That's when the whole field just collapsed.
And the weapon was a book also called Perceptrons. Minsky wasn't criticizing the hardware or the code. He was going after the core mathematical validity of the whole idea.
And the key proof he used centered on maybe the simplest non-trivial problem you can think of, the exclusive OR problem.
XR. Let's try to visualize this for a second, because this is where the axe really fell.
Okay, so imagine a simple graph with 4 points on it. You have 2 inputs. Let's say 0, 0, and level 1 are identical, so they should produce a 0 output.
Right. And the other 2 points, 0, 1, and 1, are different, so they should produce a 1.
Exactly. The network's job is to draw a line that separates the zeros from the ones. Simple classification.
But if the network can only draw a straight line, which is what a linear model like the early perceptrons did, you just can't do
You
it.
can't. There is no single straight line you can draw on that graph that perfectly separates those 2 sets of points. The pattern is just too complex for a linear model.
And Minsky mathematically proved it. He showed this simple 2-layer structure cannot solve XRR.
And that wasn't just a small problem. It was proof that the architecture was fundamentally incapable of solving even basic real-world problems, which are almost never linear.
The result was immediate. The 20-year AI winter for any research into neural networks.
But here's the tragic part of the story. The solution was already out there. It had just been ignored.
You're talking about Paul Werbos.
Yes. In 1974, Paul Werbos proposed the backpropagation algorithm in his PhD thesis at Harvard. He knew Minsky was right about two-layer nets, but he argued a three-layer network could absolutely solve XOR.
If you had a way to train it.
Right, if you had a mechanism like backpropagation to efficiently send the error signal back through the layers, Werbos saw that the third layer unlocked the nonlinearity you need.
He thought he'd found the key. But Minsky's reputation, his proof, it was just too powerful. Werbos's work was basically dismissed for decades.
It really reinforces this idea that the theory has to pave the road for the practice. The field needed a higher truth, a universally accepted mathematical guarantee, before anyone would risk their career on neural nets again.
It needed proof that the kind of function you need to solve XOR and, well, everything else was even possible to create with a layered network.
Exactly.
So to find that guarantee, we have to leave computer science completely. We're going back to 1900 to one of the giants of modern mathematics, David Hilbert.
Right, we're going from the engineering problem back to the first principle, the idea that the universe can be described by mathematical functions.
And Hilbert, at this famous 1900 Paris Congress, lays out 23 problems that he thinks will define the next century of math. We care about one in particular.
The 13th problem.
And when you first read the problem, it sounds completely unrelated to any of this. It's about solving a seventh-degree polynomial equation.
A really nasty one, with 7 variables. And the question was, can the solution be expressed using only functions of 2 variables plus basic arithmetic?
Hilbert's guess was no, right? He thought if you have a 7-variable function, you must need more complex functions inside to solve it. It's a question about complexity.
He suspected no, but the answer to his hunch is what changed the course of AI.
And the answer came in 1956 and 57 from the Soviet mathematician Andrei Kolmogorov and his student, Vladimir Arnold.
They solved it. And their result, the Kolmogorov-Arnold representation theorem, was the complete opposite of what Hilbert guessed. And it was infinitely more profound.
This is the pivot point. This is where pure math from a half-century earlier smashes right into our modern problem. What did they actually prove?
They proved that any continuous multivariate function, so any function of any complexity describing any process with any number of inputs, can be represented as a finite combination of just 2 simple tools.
2 tools, what are they?
Univariate or single variable functions, and the simple binary operation of addition.
Okay, let's break that down because this is the core takeaway. It's like proving that every single gourmet meal in the world can be made with only 2 things. A little station that can prep 1 ingredient at a time, and a big bowl to mix everything together in.
That's a perfect analogy. You take a massively complex function, one that describes climate change or the stock market, and the theorem guarantees you can break it down into thousands of tiny, simple steps. Each one of those steps only looks at a single input variable, does something simple to it, and then you just add all the results together.
So it's a radical simplification. The complexity of the universe, anything describable by a continuous function, can be reduced to 1-variable transformations, and just adding stuff up.
Yes. The theorem is incredibly strong. Even things we think are complex, like multiplication or division or exponents, they can all be rewritten as combinations of single-variable functions and addition. Addition is the only binary operation you actually need.
Which means a network of simple 1-variable functions, all connected by sums, is mathematically guaranteed to be able to describe, well, anything.
Anything.
And now we can make the final connection. Because that abstract math from 1957, solved by a Soviet team, suddenly looks exactly like the structure of a modern neural network.
The structure is unmistakable. The univariate functions are like the nonlinear activation functions in a neuron, and the addition is just the summation of the weighted inputs. It's a perfect match.
But the person who built this bridge wasn't a pure mathematician. It was an engineer in the late 1980s named Heck Nielsen.
Right. He had the aha moment. He realized Kolmogorov's theorem was the theoretical get-out-of-jail-free card.
Yeah.
It was the mathematical existence proof the neural network field had been desperate for 20 years.
He published a short paper, just 3 pages.
A tiny seminal paper that explicitly made the connection and that inspired proper mathematicians like George Sabenko to go and formalize it.
Which resulted in?
The universal approximation theorem, proven in 1989.
The UAT.
The UAT. And it states, without any ambiguity, that a neural network, provided it has enough nodes and is at least 3 layers deep.
The key Minsky missed?
The key Minsky missed. It can approximate any continuous function to arbitrary precision. It was the definitive, peer-reviewed mathematical guarantee. It proved that the nonlinearity of a multi-layered structure could solve XOR and, by extension, anything more complex.
And the engine of that guarantee is the nonlinear activation functions. The original proof specifically focused on the sigmoid function.
Yeah, the sigmoid, that little S-curve, has really nice mathematical properties. Its derivatives are easy to calculate, which is critical for training. Because of the UAT, we know for a fact that by combining enough of these individual curves, which are just simple univariate functions, we are mathematically guaranteed the ability to fit or approximate any complex function out there.
So the UAT finally gave Paul Werbos the theoretical shield he needed back in 1974. His engineering hunch was validated 2 decades later by the highest court of mathematics.
Exactly. The foundation was finally proven to be sound.
But that doesn't mean our theoretical quest is over.
Far from it. This brings us right up to the challenges of today. The Kolmogorov-Arnold theorem, and by extension the UAT, they are what we call existence proofs.
Okay, that distinction is really key. Let's use that analogy we talked about.
Right. It's like finding an ancient map that proves, without a doubt, there's buried treasure on a specific island. That's your existence proof. The treasure exists. But the map doesn't give you a shovel. It doesn't tell you the best route through the jungle or the exact coordinates to dig. That's the part that's not constructive. It guarantees possibility, but it gives you zero instructions on how to build or train the network efficiently.
And that search for the instruction manual, for the shovel, that's where all the big, frustrating, open questions in AI live today.
Exactly. You have things like the curse of dimensionality, where functions with very steep cliffs or rapid changes are technically approximable, but the computational cost becomes astronomical.
And the whole debate about network architecture. Depth versus width.
That's a huge one. We know Minsky was right that you need at least 3 layers. But is it better to add another layer or just make the existing layers wider? Research by people like Yao Kizhi is trying to quantify the trade-offs, all because the original theorem doesn't give us a guide.
And this search for a better, more interpretable, more constructive network has led to one of the most exciting theoretical ideas just this year.
The Kolmogorov-Arnold networks, or CANs, proposed by Max Tegmark's group in 2024.
What are CANs trying to do differently?
CANs are an attempt to take the original Kolmogorov-Arnold theorem more literally. Instead of using a fixed, simple activation function like sigmoid or ReLU and only learning the connection weights.
They try to learn the activation functions themselves.
Precisely. For each neuron, for each connection, the network is trying to figure out the optimal mathematical function to apply, not just the optimal weight.
So it's not just learning how much to value an input, but what kind of transformation it should perform on it.
Exactly. And this is a huge deal for interpretability, especially in fields like AI for science. If your network can tell you that a physical system behaves according to a sine function or a logarithm, well, that's incredibly useful to a physicist, much more than a million opaque weight values.
They actually tested this, right? Trying to get it to rediscover physics formulas.
They did. They had CANs perform symbolic regression on formulas from Feynman's physics textbooks to see if they could recover the underlying physical laws. It's a really promising direction.
It's just a profound feedback loop. If you step back and look at the whole history of neural nets, it has this unique rhythm. Other AI fields had the theory way before the practice. But with neural networks, it's been this constant back and forth.
A constant, sometimes angry dialogue. Engineering promise, then a mathematical failure, then a theoretical rescue from pure math.
Which leads to massive engineering practice, which is now pushing us back towards a new, more constructive theory with things like CANs.
It's been a conversation between mathematicians and engineers since the 1940s, all circling this one central question. We know a universal approximator can exist. How do we actually build the best one?
It's been a truly profound journey. From David Hilbert's abstract challenge in 1900 about seventh-degree polynomials, through the absolute collapse of the field in 1969, all the way to the theoretical bedrock of every LLM running today. The key to universal learning, it turns out, wasn't unlocked by computer science. It was unlocked by pure math, proving that any complexity can be broken down into simple functions and addition.
And the strength of our modern learning mechanism comes directly from that theoretical simplicity. It's an assurance that, in principle, any continuous relationship in the universe can be mapped and learned by a deep neural network.
And that means, for you, the learner, that while the universal approximation theorem guarantees that universal learning is absolutely possible, the search for the optimal learning mechanism, the true instruction manual for building the most efficient network, is still the great open challenge of our time. We know the treasure exists, but the search for the map continues.
还看到有学者想从根源上改进，像是麻省理工学院的物理学家 Max Tegmark，他们去年提出了一种新的科尔摩格洛夫阿尔诺尔网络 叫 KAN， 这个名字听起来就是在向源头致敬。
是的，他们团队的想法非常有趣。传统神经网络是在学习网络连接的权重，而激活函数是事先固定好的。他们就在想，有没有可能我们不只学权重，而是让网络直击去学习激活函数本身。因为激活函数的种类是有限的，如果能直接学习函数，或许能打造出结构更简单也更具可解释性的人工智慧。虽然这个方向还有很多争议，但很多人认为它可能对 AI for Science 这个领域带来重要的贡献。
回顾这整段历史，神经网络的发展路径真的非常特别啊。它不像某些领域是工程一路狂奔，然后理论在后面慢慢解释，也不是理论提出后，工程师马上就能实现。
没错，在神经网络这个领域，我们看到的是一个工程和理论交替领跑的过程。有时候是工程碰壁，等待理论突破，就像闵斯基的挑战，要等待通用逼近定理来解答。有时候又是理论先行，为工程指明了方向。这是一个非常动态、非常精彩的演进过程。
好了，我们来总结一下今天的探索。我们从一个关于7次方程式解的古老数学问题出发，看到它如何在数学家的世界里催生了一个关于函数表示的普适定理，然后这个定理又如何在数十年后，像一位天降奇兵一样，为当时陷入困境的神经网络研究提供了坚实的理论基石，最终才成就了我们今天无处不在的大型语言模型。
这段历史也提醒我们，今天 AI 所展现出的强大能力，它不仅仅是程式码和数据的堆积，在它的最深处有着非常深刻、优雅，而且是跨越了时空的数学原理在默默地支撑着一切。
最后，我们想留给你一个可以继续思考的问题。
科尔摩戈罗夫阿诺尔的定理揭示了一个非常深刻的原理，一个由大量简单单元，在这里就是一元函数和加法组成的网络，可以表示出极其复杂的整体功能。我们人类用这个原理打造了人工智慧。那么，这个数学原理是否也为我们理解自身提供了一条线索呢？我们的大脑，这个由数百亿个相对简单的神经元组成的网络，是否也是基于某种类似的数学原理，才最终涌现出了我们称之为思想、情感和意识的这些极度复杂的现象呢？